Hi everyone, welcome to Negrom seminar. Today our speaker is Virginie Ehrlacher. I hope I pronounce your last name in a
Perfect.
nice way,
Perfect. Me too.
from Paris Tech. And today she will just talk about the towards nonlinear reduced basis methods using optimal transport in electronic structure calculations. The floor is yours, Virginie. Thank you.
Thank you. Thank you very much, Virgil. And thank you a lot to the organizers of the seminar series for this invitation. It's a great pleasure to give this talk here. So today I'm going to talk about some nonlinear reduced basis methods, as the title says, for electronic structure calculations, which uses optimal transport theory concepts. And this is joint work with my colleague, Geneviève Dusson from CNRS, with her PhD student, Maxime Dallery, Alexei Lozinski, and Etienne Pollack, who is a postdoctoral student at École des Ponts. So first of all, I would like to say a few words about the context and the motivation of our work. Here, what we want to do, we want to accelerate some electronic structure calculations, the aim of which is to compute the state of electrons within a molecule. So let me first give you a brief recap of what are the different objects of interest here. So the molecules we're interested of are composed of nuclei. So nuclei are quite heavy particles composed of protons and neutrons, okay? And they are on these pictures, they are represented with these big balls, okay? So on the left-hand side, you see the H2O molecule for water. So the big red ball is the oxygen nuclei, and the two white balls are the hydrogen nuclei, for instance. And classically, in what's called the Born-Oppenheimer approximation, these nuclei are assumed to be classical point charges. And together with these nuclei, we also have electrons, which are much lighter particles than nuclei, and cannot be modeled at the scale as classical particles. They have to be modeled as quantum particles. And you have, if you're not familiar with this, with quantum mechanics and so on, you can imagine them as forming some kind of cloud, a gluing cloud, which helps the molecule to remain, the different nuclei of the molecule to remain bounded, okay? So more precisely, why are we interested in computing the state of electrons within such molecules? We are interested in computing this kind of thing because the state of the electrons within a molecule account for many of its properties, electrical, optical, magnetical properties. It also accounts for the different chemical reactions that may occur between different molecules. And in addition, knowing how the electrons arrange around the nuclei of a molecule helps in building what's called interatomic potentials that can be used in simulations at a larger scale, where one wants to know how molecules will interact with each other. And this is called the molecular simulations. And these types of simulations are used widely in order to try to explain how matter behaves on the macroscopic scale out of the knowledge of the interaction between the different molecules which compose the material at a microscopic scales. And here, and there are different models to try to compute approximations which help in having some ideas on how the electrons will arrange within a molecule, including the Schrödinger's or Hartree-Fock models, for instance. I don't want to go too deep into this. There's a wide zoology of models. Okay. And here, in this talk, I'm going to make a specific focus on the computation of the ground state of electrons. That is to say, it is the state of the electrons which have the lowest possible energy within a molecule. So it's one information about the state of the electrons. It's not the only information that is interesting from a material science point of view, but from this ground state, you can still have access to a very, very large number of properties of these molecules. So for the sake of simplicity in this talk, I'm going to focus on this particular ground state. I forgot to say, if you have any questions, please do not hesitate to interrupt me and ask it during the course of the talk. I mean, it's feel free to interrupt me anytime. So now that I've explained to you, let's say, the main context of this work, I need to introduce a few notation to explain to you what are the mathematical models that enable to compute the state of the electrons, these cross states of the set of electrons. So here, let me precise a little bit some notation. So I'm going to assume that I consider a molecule which is composed of M nuclei, okay? So as I told you earlier, these nuclei are quite heavy particles, and they can be modeled as classical particles. Their positions will be denoted by R1 up to Rn, and they will be vectors belonging to R3, okay? And they will be also characterized by their electric charges, which will be denoted by Z1 up to Zn, and these are positive electric charges, okay, since nuclei are composed of protons and nucleons, remember. Okay, so I assume that this quantity R1 up to Rm and Z1 up to Zm are enough to characterize the nuclei within my molecule of interest. And now let me assume that there are also, in addition, n electrons, okay? So as I told you, these electrons, they cannot be modeled at the scale as classical particles. They have to be modeled using concepts of quantum mechanics. And more precisely, the state of this set of n electrons will be represented by a quantity which is called a wave function, okay? That is a function psi, which will depend on n vectors of R3 denoted here by x1 up to xn. Sorry, before I proceed, can you see the arrow here that I'm moving?
Yes,
yeah, you can see it, right?
Yeah. Yes.
Yeah, okay, thank you. And so this wave function is complex valued, and it encodes all the information you might need to characterize the state of these n electrons within the molecule, okay? Before I proceed, let me make the following point also. It holds that this wave function psi has to be antisymmetric with respect to the ordering of the vectors x1 up to xn, with respect to permutations of electrons within themselves. Okay, why is that? This is due to the fact that electrons are fermionic particles. And to make a long story short, this encodes the so-called Pauli exclusion principles, which states that you cannot find two electrons at the same place with positive probability. And so this antisymmetry somehow encodes this Pauli exclusion principle. Okay, so for those of you who are not familiar with quantum mechanics, let me just mention the following fact. So psi is complex valued, okay? This function is complex valued, but if you consider its squared modulus, so the squared modulus of psi evaluated at x1 up to xn, so remember here again, x1 up to xn are vectors of R3. This represents the probability density of finding the n electrons at positions x1 up to xn, okay? So because here at the scale within quantum mechanics, you cannot say that the electrons will be located at deterministic positions into space. This wave function, so you can only have access to some probabilistic information on the set of electrons, and this is encoded into the square modulus of this wave function psi. Okay, and the consequence of that is that if you integrate over R3n the squared modulus of the wave function, because of this interpretation as a probability density, this necessarily has to be equal to 1, okay? This is the probability that you will find the n electrons somewhere in the space. And this is, of course, equal to 1. Okay? I need also to introduce a few other quantities. In particular, what is called the electronic one or two body density. So let me first, so you have a look at what's happened at the left-hand side bottom part of the slide, okay? So the electronic one body density, what is it? It is this quantity, rho of x, so it will be a function which will depend on x, which is just a vector of R3, by contrast to the wave functions, which depends on n vectors of R3, okay? And it's equal to the integral of the squared modulus of the wave function psi integrated over all vectors of R3 except one, which is x, okay? So this is a function only defined on R3 by opposition to the wave function, which is defined on R3n, okay? And similarly, you can define what's called the, rho of x denotes the probability density of finding one electrons at position x among the n possible electrons. And similarly, you can define what's called the electronic two-body density, which is this quantity 2 of xy being two vectors of R3, and which is also the integral of the square modulus of the wave function integrated over all variables of the wave function except two vectors of R3. Okay, so in a nutshell, tau of xy encodes the two-body correlation effects within the set of electrons. Okay, so just keep in mind these two quantities that will be that will be important in the sequel. Are there questions so far? I hope it's fine. So just keep in mind that my the state of my system of n electrons is encoded by such a wave function psi, and that important quantities are these electronic one-body or two-body densities. Okay, so as I told you, what we are focusing on in this work is the ground state of the set of electrons in my molecule. That is to say, the state of the electrons that has the lowest possible energy within the molecule. And this ground state will be characterized by some wave function, here denoted by psi r, okay? So more precisely, here r in bold letter will denote the collection of the positions of the nuclei in the molecule, R1 up to Rm. And so this bold R letter will be a vector belonging to R3n. Okay, so it's a collection of the set of positions of all the nuclei within the molecule. Let me introduce Vr of x. So it's a function which depends on the positions of the different nuclei within the molecule, R, and which depends on one vector of R3, x. And it's defined in the following way, and it's equal to the Coulombic potential generated by the nuclei into space. Okay, so you see here, Zk is a charge, electronic charge of the kth nucleus, and Rk is the position of the kth nucleus. And you make the sum of all these Coulomb potentials over all the nuclei in the molecule. Okay, so keep that in mind. Then the ground state electronic wave function, psi r, which characterizes the state of with lowest energy of my set of n electrons, is given as a solution of the following parameterized eigenvalue problem, okay? HR psi r is equal to ER psi r, where HR is an operator, which is called the Hamiltonian of the system. It's given by this formula here, okay? And you see that there is this middle term, which where the different contributions of the Coulombic interaction potentials of the nuclei on the electrons appear, okay? And you've got two other terms. The first term, which is the Laplacian, encodes the kinetic energy of the electrons. The right-hand side term encodes the energy due to the Coulombic interactions of electrons within themselves. And the middle term encodes the energy linked to the Coulombic interactions of the electrons with the nuclei of the molecule. Okay? And this Hamiltonian, this operator, is parameterized by the set of positions of the nuclei in space. And its lowest eigenvalue, ER, is then the energy associated to the set of electrons, the state of which is characterized by the wave function psi r, which is an eigenvector of this Hamiltonian, parameterized Hamiltonian. Okay, so there is quite a challenge in the case where the number of electrons is quite large, which is that solving this equation actually amounts to solving a linear problems, the solution of which is a function which is defined on R3n, which is a very high dimensional space. Okay, but here keep in mind that what we want to do here is to approximate solution of such problems when R, the set of positions of the nuclei, will vary. Okay, and this collection of positions of the nuclei will play the role of parameters in my problem. And that's the problem for which we want to develop some reduced order modeling techniques. Okay, so that's exactly what I wanted to say. So in practice, we will not directly tackle this linear eigenvalue problem, which is well defined on much too high-dimensional state space. In practice, what chemists do, they rather rely on approximate models, which are approximations of the model I just introduced to you. Okay. The solution of which is only the one-body electronic density associated to this wave function psi r. Okay, so remember the one-body electronic density was defined out was this quantity rho of x. Okay, defined out of a wave function psi with this formula here. And so in practice, what chemists do compute, they do compute this one-body electronic densities. They don't compute the total wave function. Okay, but here I'm going for the sake of simplicity, I'm only going to consider some time models, okay, where the solution of which will be these wave functions. But keep in mind that here I'm only focusing on toy models, but in practice, one would only have access to the one-body electronic density. And what we want to do, so we want to build some reduced order models in order to accelerate computations of these quantities, either one-body electronic densities or wave functions, and the parameters will be the set of positions of the nuclei of the molecule. Okay. And there is one very important property, which is that if you translate all the nuclei of your molecules from one given translation vector, B, then your wave function or your electronic one-body density will be translated by the same translation vector. Okay, and so this is a property that we want the reduced order models to satisfy. Okay, to preserve. And that's the reason there are similar issues in reduced order modeling techniques for transport-dominated problems. And that's the main reason why we decided to use some techniques belonging to optimal transport theory to build reduced order models that will indeed satisfy this type of properties. Okay, so here the goal here is to build some reduced order model in order to approximate M, the set of solutions. And here, for the sake of simplicity, I'm only going to assume that my set of solutions is the set of wave functions. Here, sorry, this should be a small psi, not a big psi. Solution to this type of parameterized eigenvalue problems, where the parameters are the set of positions of the nuclei, and these parameters belong to some parameter set, which I denote here by calligraphic. Okay, and so I'm going to explain to you the type of techniques that we use for this particular problem. Okay, so just to mention a few works, there are lots of works which use optimal transport theory to build reduced order models in various application fields. So the very first work I'm aware of where these concepts are used is a work by Angelo Iolo and Damiano Lombardi, where they used, so we're building transport maps as linear combinations of optimal transport maps, let's say. There have been some works then with Damiano, Olga Mula, and François-Xavier Vialard on the use of Wasserstein barycenters for transport, parameterized transport problems. And there are also various different extensions and refinements of this type of techniques in different directions. Here, the list is far from being exhaustive. Just to mention that there is a vivid activity on the field of reduced order modeling techniques using optimal transport theory. And somehow this is another contribution in this direction that I'm talking about. dedicated to electronic structure calculations. Okay, so here in the rest of the talk, I'm going to make a specific focus on a toy model problem, okay, which will be a toy one-dimensional model problem. The reason for why we are interested in this toy model is first that we can prove theorems, okay, related to the techniques that we have developed for this problem here. And the second reason, which is the most important, is that it encodes in a quite faithful way the inherent difficulties of three-dimensional electronic structure calculations, in the sense that the wave function will depend on the set of positions of the nuclei in this 1D toy model is quite relevant to understand how the true wave functions or the true one-body electronic density will vary as a function of the positions of the nuclei of the molecule in a real 3D test cases. So this is a simplistic model, toy model, indeed, but it encodes a lot of physics in there. Physics that is present when you want to tackle true actual molecules. So for this toy one-dimensional problems, there is one convenient thing, which is that we know the analytic solutions. Okay, so here you see this is the solution of this toy model are still solutions of the parameterized linear eigenvalue problems. And this psi r, we know analytically how they write. Okay. More precisely, these wave functions, they read as some positive combinations of functions, okay, which reads here as ladder functions. So they are written as a linear combinations of functions of the form exponential minus some coefficient zeta r times the norm of x minus rm, and rm is the position of the nth nuclei in the molecule. And we know precisely what's the value of this coefficient zeta r here and this coefficient pi mr. There are analytical formulas that gives them. Okay. And this was crucial in order to prove the theorems that we were able to prove on the techniques that we have developed. So just to give you, some ideas of what these functions look like, here are some plots of these wave functions for different values of the positions of the nuclei, okay, and different values of the electric charges of this nuclei. So you see they have these typical peaky shapes, okay, and the locations of the different peaks coincide with the location of the different nuclei in the molecule, okay. And you see, well, as you move the positions of the nuclei, well, the location of the peaks may move, as well as their amplitude. Okay, so let me first make a brief. Sorry. Let me make some brief sentences about what happens if you want to use linear reduced order modeling techniques for this type of problems. Okay, so this is I guess everybody here attending the talk is quite familiar with this type of concepts, but just for the sake of clarity, let me precise this. Okay. So if you wanted to use linear reduced order modeling techniques to build reduced order models for this type of problems, the typical way one would proceed is the following. One would find some wisely chosen parameters, L1 up to Rk, among the set of possible values of the positions of the nuclei into the range of parameters values that I'm interested in, okay? And one would try to compute an approximation of the wave functions for a new set of positions of the nuclei as a linear combinations of the wave function computed for this particular chosen values of the parameters. Okay. And the natural question that one can ask is, whether it may be efficient to do such a kind of a procedure. And the efficiency of this type of linear reduced order modeling technique, so I guess everybody is familiar with this, it is encoded in what's called the Kolmogorov n width of the solution set. So here, remember, n is the solution set of my parameterized eigenvalue problem. So it's a set of my wave functions, when the set of positions of my nuclei vary into the parameter space. And here, this quantity, the n of mh, encodes how well I can approximate solutions belonging to the solution set by elements belonging to some small dimensional subspace here by some small dimensional subspace, the dimension of which is equal to small n. Okay, and if this n Kolmogorov width decays rapidly with n, this says that linear reduced order modeling techniques can be efficient to approximate my solution set. So this is the case in particular for elliptic equations. Okay, I don't want to spend too much time on that, but we know that for certain types of problems, these linear reduced order modeling techniques are not efficient. For instance, for parameterized transport equation. So this is a classical result. Okay, we know that that this Kolmogorov n width for the solution of parameterized transport equation of the following form typically decays at a rate which is not better than 1 divided by the square root of n, which is quite slow. Okay, so here in this one-dimensional toy problem for electronic structure calculation, so really the eigenvalue problem I presented you, we know the speed of decay of the Kolmogorov n width in some particular case. Okay, so typically when there is only one nuclei, okay, and you make its position vary into an interval of parameters, well, we know that the Kolmogorov n width of the solution set decays exactly at the rate given by n power minus 3/2. So it's a bit better than for the parameterized transport case, but it's still quite slow. And we can prove a similar result in the case when you've got two nuclei, the positions of which can vary into some random values. Okay, so in that case, we know that the Kolmogorov n widths cannot decay at a speed greater than this n minus 3/2 as well. We don't have an upper bound like in the one nuclei case, but we know that it cannot decay fast. Okay. So linear reduced order modeling techniques are not efficient for this type of problems. Okay, because that was somehow to be expected. And that's one of the reasons why we turn to reduced order modeling techniques using optimal transport. Okay. And in particular, we would like the reduced order modeling technique to take into account the fact that when you translate a set of nuclei of the molecule, the wave function and the one-body electronic density are translated in the same way. And this is one interesting property which is encoded into a concept of optimal transport, in the sense that if you look at an interpolation between two translated Slater function of this form, so this Slater function, remember, the wave function of the form exponential minus absolute value of x. And if you look at two such functions, optimal transport theory provides a way to interpolate between two such translated snapshots by just slowly translating the one snapshot onto the other, as is illustrated by this red function here. And this is a nice property that we want to exploit in what I'm going to say. Okay, so for this, I need to make a brief recap on optimal transport theory. So here, I'm going to denote by P2 of R. It would be the set of probability measures on R with finite second order moments, okay? And the solution of my parameterized eigenvalue problems in the one-dimensional toy model will belong to this set, okay? So the Wasserstein distance is a distance defined between two elements of this set of probability measures. It is for UV two such elements. It is defined as follows. So it's a quantity denoted by W2 of UV. And this quantity squared is defined as the solution of some minimization problem over the set of probability measures pi defined over R to the squared with marginal densities given by U and V. Okay. So the proper definition of this Wasserstein distance, if you have never encountered it, it's not very important if you don't remember it for the sake for the rest of the talk. Okay, but that's the proper definition. Just remember that it is a way to measure a distance in some particular way between two probability densities, defined on R. Okay, and you can consider barycenters with respect to this particular Wasserstein distance. So more precisely, what do I mean by that? I assume that I've got a collection of probability measures. So this collection of probability measures will be denoted by bold U. It's a collection of Q probability measures denoted by U1 up to UQ. And I assume that I'm given a set of barycentric weights. So they are denoted by this letter bold T. And it's a collection of weights T1 up to TQ, which are non-negative and which sum to 1. Then one can consider the following minimization problems, which consist in looking for the best probability density U in P2 of R that minimizes the sum from Q equal 1 to BQ of these weights TQ times the Wasserstein distance squared between U and UQ, one of the elements of the family of measures squared. Okay. You can ask yourself whether there exists one probability measure which minimizes this quantity, and indeed there is one, and it is unique. And it's called the Wasserstein barycenter of the collection of measures U1 up to UQ associated to the barycentric weights T1 up to TQ. I just want here to make an analogy between this Wasserstein barycenter and what would be an L2 barycenter if my collection of probability measures were assumed to belong to an L2 spaces. Okay, so here consider the same minimization problem, but instead of having the Wasserstein distance here, you put the L2 norm between U and UQ of U minus UQ here in the minimization problem, you see? So you consider a Euclidean norm instead of this Wasserstein distance. Then for the latter minimization problem, you know what is the unique minimizer. It is simply the linear combination of the UQ probability densities with weights given by TQ. Okay, and this is what the type of barycenters that we know more classically. Okay, so just remember that this Wasserstein barycenter, it plays the same kind of role as the classical barycenter that you know in a Euclidean space, except that here it is a notion that is adapted to this Wasserstein metric I just told you about. And these Wasserstein barycenters will be key in the reduced order modeling techniques I'm going to tell you about. So for one-dimensional probability distribution, there is an easy way to compute this Wasserstein metric and to compute these Wasserstein barycenters. And this is possible by means of the inverse cumulative distribution function associated to the probability distributions. Okay, so more precisely, if U is a probability density belonging to the set P2 of R, I can define the cumulative distribution function CDFU, which is a function with some x belonging to R, associate the integral between -∞ and x du. Okay, and I can consider the generalized inverse of this function. Okay, and this quantity then is a function which maps the interval 0, 1 onto R. Okay, and these inverse cumulative distribution functions, then you can prove that they are squared integrable functions, and you can express the Wasserstein distance between two probability densities U and B as the L2 norm of the difference between their ICDFs, their inverse cumulative distribution functions. Okay, so this is an easy way to characterize this Wasserstein distance by means of these inverse cumulative distribution functions. And you can similarly have an easy characterization of the Wasserstein barycenter by means of its ICDF, okay, in the sense that the ICDF of the Wasserstein barycenter of a family of probability distributions associated to a family of barycentric weights, while it's just the linear combinations of the ICDF of all the elements of the family of probability densities with weights here TQ. Sorry, there is a typo. This is TQ. And so you have an explicit characterization of this Wasserstein distance and barycenters by means of this ICDF. Okay, so just to give you an idea of how this Wasserstein barycenters, what they look like, okay. Here consider two probability densities, one in orange and the other one in blue. And you see here was a green curve represents the Wasserstein barycenter between these two probability densities when you make the barycentric weight vary, basically here from 0 to 1. So this is what happens on the left-hand side figure. You see the probability densities and interpolated probability densities. On the middle figure, you see the cumulative distribution functions associated to these probability densities, and the ICDF are plotted on the right-hand side figure. And you see in particular that indeed this Wasserstein barycenter encodes in a nice way some translational properties of the different probability densities. Okay. Okay, I want also to make one particular point. When one considers one specific family of probability measures, that's called the location scatter probability measures. So what are they? Here, A, calligraphic A, will be the set of probability measures that are computed as affine transformations of one reference measure, which is denoted by small a here. Okay. Here, small a will be the Slater distribution function defined by means of this exponential minus absolute value of x here. Okay, and this calligraphic A will be all the set of probability measures that you can compute out of translations and dilatations of this reference probability measure. Then you can have very simple expressions for the Wasserstein distance between two such probability measure, which can be explicitly expressed by using the means and the covariance matrices of this location scatter probability measure. And so you've got an analytic formula for this Wasserstein distance. And you can also have very simple expressions for the Wasserstein barycenters, in the sense that for the mean of the barycenter will be the barycenter of the means, okay? And you have a very simple expression as well to give the covariance matrix of the Wasserstein barycenter in this very particular case. So in this case, you don't even have to use ICDFs to compute this Wasserstein distances and Wasserstein barycenters. So here, just to give you some plots, here you see some isolines, some contours of 3 different Slater distributions, and the Wasserstein barycenters associated to some barycentric weights for this family of 3 Slater distributions is given by this middle Slater distribution. Okay, so now one can ask the following question. If instead of considering the Kolmogorov n width of my solution set of my parameterized eigenvalue problem with respect to an L2 metric, as I did for previously when I mentioned linear reduced order models. Okay, sorry, I'm trying to find the slides here. You see, I was considering the Kolmogorov n width with respect to an L2 metric. One can ask yourself whether I can have better decay of a similar quantity, but this time defined by means of this Wasserstein metric instead of the L2 metric. So more precisely, I can define a Kolmogorov n width of my solution set associated to the Wasserstein metric. I can define it as the Kolmogorov n width of the set of ICDFs of my solution set with respect to the L2 of 0,1 metric. And the question is, if I now consider this type of modified Kolmogorov n width adapted to this Wasserstein metric, do I obtain better rates of decay? And the answer is yes, in the following sense. In the case where there is only one nuclei, it's easy to show that indeed the Kolmogorov n width, this Wasserstein Kolmogorov n width, will be equal to 0 as soon as n is greater than 2. Okay, so it's very easy. And now in the case of two nuclei, one can prove that this Kolmogorov n width decays like n to the minus 5 divided by 2. Okay, which is a bit better, which is an improvement with respect to the linear Kolmogorov width, which could not decay faster than n to the minus 3. Still, it's not exponential, okay? It's still algebraic rate, but better rate than for linear reduced basis, linear reduced order modeling techniques. Okay. However, we face some limitations with this Wasserstein metric. And this limitation is the following. Here I've told you about the situation in 1D, okay? But if you want to go to higher dimensions, that's what we want to do for the true electronic structure calculations. Computing these Wasserstein barycenters and these Wasserstein metrics is can be quite costly from a computational point of view, okay? And it scales quite badly with the dimension of the problem. So for 3D electronic densities, it just wouldn't be affordable, okay? And in addition, this approximation property, so the fact that the Wasserstein Kolmogorov n width decays like n to the minus 5 half, well, it's not great, okay? We can hope to do better than such an algebraic weight. And that's the reason why we considered another metric, which is a modified Wasserstein metric, but which is dedicated to a particular subset of probability measures, okay? And this particular subset of probability measures will be built out of this location scatter probability measures I told you about. So remember, A was a set of probability measures that I can compute as dilatation and translations of one single reference measure. And here's the reference measure that's of interest to us is this latter function, exponential minus absolute value of x, okay? And so this modified Wasserstein metric will be a metric between two probability measures, which will read as a mixture of such location scatter probability measures, okay? So more precisely, this will be a modified distance between two probability measures, mu0 and mu1, that can be written as convex combinations of location scatter probability measures, that is to say, of translations or dilatation of this reference slatter, the slatter probability measure, okay? And this modified metric is defined as follows, okay? So the expression is a bit complicated. Just want to highlight to you the ingredients that are necessary to compute it. So to compute this modified distance between two such mixtures, you only need to know the Wasserstein distance between each location scatter measures that appear in the convex combinations, okay? So between all these A0J, A1K. But this, as I told you before, this can be computed analytically out of the knowledge of the means and covariance matrices of this location scatter probability measures. So this guy is very, very easy to compute. And there are weights here, this WJK, that actually are solution to some linear programming problem, okay? And the complexity of the resolution of this linear programming problem doesn't depend on the dimension of the underlying space, but only depends on the number of terms into the mixture, okay? On the number of terms in the definition of this mu0 and mu1 probability measures. So the dimension of the underlying space does not come into play in the computation of this modified Wasserstein metric, only the number of terms in the sum, basically. And this is a nice thing for us. And so instead, we wanted to look, okay, now we know on our 1D toy model that the solution of our parameterized eigenvalue problems are indeed mixtures of this location scatter probability measures defined out of a scatter, a reference scatter probability distribution. What happens to the Kolmogorov width of our solution set when we define it with respect to this modified Wasserstein metric and not the exact true Wasserstein metric? And so that's what we try to analyze. Just forgot to mention, you can define in a very similar way some modified Wasserstein barycenter as barycenters with respect with this modified Wasserstein metric. In exactly the same way as you would define the Wasserstein barycenter with the exact Wasserstein metric, you can have exactly the same kind of concept of barycenter with this modified Wasserstein metric. And what is very interesting is that this modified Wasserstein barycenter remains a mixture of scatter distribution function, which is not the case of the exact Wasserstein barycenter of scatter distribution functions, which may not be scatter distribution functions anymore. Okay. And in addition, computing these barycenters is way cheaper than computing exact Wasserstein barycenter. And the dimension of the underlying space doesn't come into play anymore in the complexity of the computation of these modified Wasserstein barycenters. So just to give you, just to give you an idea of how these barycenters look like, this is a set of pictures. So here we looked at mixtures of location scatter probability densities not defined with scatter functions, but with Wigner semicircles probability distribution. But still, you can have a hint of how this barycenter look like. So you see on the left-hand side and right-hand side, you've got two mixtures, two different mixtures, okay, which are identical, okay. And we look at the Wasserstein and modified Wasserstein barycenters between these two mixtures using either the exact Wasserstein metric or the modified Wasserstein metric. So the exact Wasserstein metric barycenter is represented in the bottom line of the figures, and the modified Wasserstein metric is represented in the upper line of the figures. And what you see is that indeed, on the upper part, these modified Wasserstein barycenters remain mixtures of Wigner semicircle distributions, whereas the exact Wasserstein barycenter looks quite weakly, okay? And this, for the electronic structure calculation applications that we're interested in, well, it's not good. It's not a good news for the exact Wasserstein barycenters, because indeed, the solution of the electronic structure calculations are, that's what we observe, and that's what I'm going to show you. They are much closer to these modified Wasserstein barycenters than to the exact Wasserstein barycenters. And this can be expressed as a theorem using our toy one-dimensional problem, okay? So in that case, you can define a Kolmogorov n-width concept associated to this modified Wasserstein metric. And what you can prove is that this modified Wasserstein Kolmogorov n-width for our one-dimensional toy model, in the case of two nuclei, while this modified Kolmogorov n-width is just equal to 0 as soon as n is greater than 2. So you can represent exactly the solutions of our toy one-dimensional problem as a modified Wasserstein barycenters between two snapshots. And indeed, this proves the interest of using this modified Wasserstein metric by comparison with the exact Wasserstein metrics for which we only had this type of algebraic decay. So this modified Wasserstein metric has two advantages. One, it's easier to compute, and it's easier to compute barycenters with respect to the modified Wasserstein metric, and it has better approximation properties for the electronic structure calculation problems that we are interested in. And this we are able to prove on this one-dimensional toy model. And that's something that we want to exploit for more realistic applications with true molecules and higher dimensional test cases. So let me just conclude by some numerical results on the one-dimensional toy problem I told you about to illustrate the practical interest of the strategy. So in practice, basically, to develop a nonlinear reduced order model, so what we do is a greedy algorithm to select some particular values of the parameter sets. Okay. So it's a greedy algorithm adapted to this mixture Wasserstein metric, modified Wasserstein metric I told you about. Okay, but the principle is exactly the same. You've got a set of snapshot solutions, and among this set of snapshot solutions, you select a few of them using a greedy algorithm adapted to this modified Wasserstein metric, and then in the online part, so this is the offline part, and in the online part, you compute approximate solutions as barycenters of these few selected snapshots. And these barycenters are barycenters with respect to this modified Wasserstein metric. Okay, so for the sake of time, I'm not giving too much detail. I just want to make one precision on the online strategy. So as I told you, we compute solution of the reduced order models as barycenters of a few snapshots with respect to this mixture Wasserstein metric. Okay, so but we have to compute weights to define these barycenters. What are the good optimal weights? And these weights, since this mixture Wasserstein barycenters are are defined the way as they are, actually they are a solution of a non-convex optimization problem. So that's one weak point of the approach, in the sense that we have to find some numerical strategy to solve this non-convex minimization problem. What saves us is that they are non-convex problems, okay, but in rather low dimension. So here in practice, in the numerical tests that I'm going to show you, we basically use some quasi-Newton method starting from different initial guesses to try to find a good optimizer of the non-convex optimization problem. Well, that's there probably are some better approaches, but that's the one that we used here, and it proved okay for our purposes. So now here are some plots of how the error decays with the number of selected snapshots by the greedy algorithm. Okay, so I have my one-dimensional toy model with two nuclei there, and I make the positions of the nuclei varying to some range of values. Okay, and I'm looking at how my reduced order model performs in terms of the mixture Wasserstein distance. In the sense, here I'm computing the mixture Wasserstein distance between the exact solution of my problem and the solution given as the output of the greedy algorithm based on this mixture Wasserstein metric, okay? As a function of the number of snapshots selected by the greedy algorithm. And here what you see is that this error seems to decay exponentially with respect to the number of snapshots, which is quite good news in contrast to the algebraic decay that we were able to prove with either linear reduced order modeling techniques or the use of the exact Wasserstein metric. So here, the use of this modified Wasserstein metric is quite interesting in terms of approximability properties of the solution set. And these are how the different snapshots selected by the greedy algorithm look like. Okay, these are the 8 first snapshots selected by the greedy algorithm. And this is an example where the exact solution of the eigenvalue problem for one value of the set of positions of the nuclei in the molecule is given. So this is a blue curve, which is hidden by the purple curve. Okay, and here you see how well this solution is approximated when you use a mixture Wasserstein barycenters of the 2, 4, or 6 first snapshots selected by the greedy algorithm. And there you see that with 6 snapshots, we've got quite a good agreement between the true solution and the modified Wasserstein barycenters of the 6 snapshots selected by the greedy algorithm. Okay, here is the error in the eigenvalue, which is the energy of the set of electrons. And you see the typical, the same kind of decay as for the error on the eigenfunction as well. Okay, so it's it's quite encouraging results for this type of problem. This is another instance of a comparison between the exact solution of the toy 1D problem and its approximation as a mixture Wasserstein barycenter. So here, just I would like to summarize and finish with this. What are the key points in this type of approach? First, the use of this modified Wasserstein metric is much more suited to the parametric dependency of the problem than the use of linear reduced order modeling technique of an exact Wasserstein metric. And this is actually, so this is something that I highlighted in this toy one-dimensional problem, but this is something that will probably be also the case for higher dimensional cases with actual molecules in 3D. And what is nice is that the complexity in computing these modified Wasserstein barycenters is independent of the underlying dimension of the space. It only depends on the number of components into the mixtures, which depends on different probability distributions. So that's pretty nice when we want to do, since we want to go to actual molecules with this type of approaches. The limitations is that we need the probability distributions in the solution set to have a specific structure, in the sense that we need them to be mixtures of this type of location scatter probability distributions, okay, which is, of course, it's not the case for any type of applications. Of course, this is very a specific case of this electronic structure calculations setting that I told to you about. One extension of this work is, of course, to carry out this technology to accelerate electronic structure calculations for actual molecules. So this is work in progress. And also another line of ideas that we would like to pursue in the future would be not only to accelerate the computations of electronic densities or electronic wave functions, but also to accelerate the computation of what is called density matrices that are actually operators that are orthogonal projectors. So I'm here making a long story short. But there, instead of computing solutions that are probability measures, you will need solutions that are operators and orthogonal projectors. But you can use, there are some concepts in quantum optimal transport in theory that enable to define similar notions as these Wasserstein barycenters that I told you about for probability measures, which are adapted to these orthogonal projectors. So that's something that we would like to do in the future. So as a conclusion, I presented you some nonlinear reduced order modeling technique for electronic structure applications based on the use of modified Wasserstein barycenters that are mixture Wasserstein barycenters, which have better approximation properties than the exact Wasserstein barycenters. And this, so far, we have only carried out the mathematical analysis a numerical test on one-dimensional toy models. But in principle, the method should scale with the dimension, and we are currently carrying out this type of technology on actual molecules. So with this, I just would like to make a shameless advertisement. We have some PhD and postdoc positions open in our lab on reduced order modeling techniques for electronic structure calculations in general. So if you are interested, don't hesitate to contact me. And thank you a lot for your attention.
Thank you so much, Virginie, for such a nice talk. And let's hear some questions or comments from the audience. If no, I can just ask one. On page 11 or page 30, which one is easier for you? You just pointed out
this one, for instance?
11, yes. In offline part, you say that you need to just choose your foam, let's say foam solutions for wisely chosen parameters.
Yeah.
Could you just explain a little bit, I mean, that what is the criteria to just get what do you mean exactly for wisely chosen parameters? I mean, that what could be at the worst case if you pick the wrong snapshots?
Yeah. So typically in practice, where these parameters are selected using a greedy algorithm, but you can define such a greedy algorithm depending on the metric that is the most relevant to your problem. So the classical way for linear reduced order modeling technique would be to use a greedy algorithm with the L2 norm, basically, saying the solutions of a problem as solutions belonging to an L2 space. Okay, so this is the most standard way of choosing these parameters. Or you can devise a greedy algorithm where instead of computing the errors that you make in an L2 sense, you can use this Wasserstein metric or this modified Wasserstein metric. Okay. And this gives rise to another selection of parameters, okay, which is adapted to the choice of the metrics that you make, L2 Wasserstein or modified Wasserstein. And so here in the linear reduced order modeling, here I was thinking more about an L2 type of metric.
I see. Thank you so much. And I think Trajan has a question.
Yes, very nice talk, Virginie. So I like how you try to explain the background, and so this is greatly appreciated. So what my question for you is relative to the computational cost. So I think you talked a little bit about this, but I was just wondering, so how would this what's the computational cost you think? So you looked at one-dimensional problems, but you said that you're working on the actual higher dimensional type of problems. And if you have any insight into like how the computational cost is gonna scale for those type of problems, and
Yeah, so perhaps I'll comment on first, if we were to use the true Wasserstein metric. Sorry, to compute typically this Wasserstein barycenter, we would need to rely on a discretization grid of R3. Okay. And the typical size of this discretization grid would be well, let's say for not too precise calculations would be 100 times 100 times 100. Okay. And this would lead to a cost typically which would scale like 100 to the 6, which is way too large for what we want to do. So exact Wasserstein barycenters are not usable in that case. However, with this modified Wasserstein metric, the cost is only related to the number of terms here. You see, so we restrict the set of possible solutions that we can consider. okay, which are convex combinations of particular probability distributions, okay. But these probability distributions could be probability measures on R3, okay, on R6. That would be the case if we want to approximate the two-body electronic densities. It's not a problem because the cost will only be related to the number of terms in this sum. And for the electronic structure calculations we're interested in, they remain quite slow, okay, let's say a dozen, not more. And in particular, the Wasserstein distance, you see this quantity here, because you consider very particular types of probability distributions that are these location scatter probability measures. This Wasserstein, the quantities that appear here are explicitly computable out of the means and out of the covariance matrix. So this is very straightforward. And this is why this modified Wasserstein metric is very interesting in order to upscale to real life applications. And that's what we are currently doing. So the cost will be related to the number of terms in these sums here. And for molecules of with not too many nuclei, let's say, but with let's say medium complex molecules with tens, dozens of nuclei, this number of terms scales linearly with the number of nuclei, basically. So for, let's say, complex, medium complex molecules, this is still okay. And it's much quicker to compute than techniques that would require the use of discretization grid of R3 space. This
Right. Thank you.
I had another question on slide 23.
Yeah.
A couple of slides before. You discussed this comparison between the two different approaches for n equal to 2.
Yeah.
But if I look at the inequalities, one of them is an upper bound and the other is a lower bound. Can you give us an intuition on why is it that in one case you're able to get the proof of the upper bound and in the other the lower bound?
Yeah. So here it's a linear Kolmogorov width. Okay, so there are three quantities. There is the linear Kolmogorov width, which we know will decay slowly, okay, because of the lower bound. There is the exact Wasserstein Kolmogorov width. So we know it decays quicker than the linear Kolmogorov width, but it decays slower than the mixture Wasserstein Kolmogorov width. So in the sense that for the mixture Wasserstein Kolmogorov width, always in the case of two nuclei. For more nuclei, okay, we don't know. But for two nuclei, we know that with this mixture Kolmogorov width, the Kolmogorov width associated is 0 as soon as n is greater than 2. And we know that this is not the case with the exact Wasserstein Kolmogorov width. It will not be 0 for n greater than 2. It could decay faster than this n to the power 5/2, but this may not be optimal rate, okay? But we didn't manage to prove better. And to be honest, I'm from what we saw in numerical tests, I don't think it will decay very rapidly, this exact Wasserstein Kolmogorov width. It will remain an algebraic rate. That's what we see on this particular test case. So perhaps the -5/2 is not quite optimal, but it will not be a super fast decay either. And this is, in my opinion, related to this type of shapes of the barycenters. So is the bottom part here is typically an exact Wasserstein barycenter, and you see that there are some strange wiggles which you do not see when you use a modified Wasserstein barycenters. And that's what we are able to say at this point.
Okay, thank you.
If there is no further question, let's thank our speaker again. Thank you so much, Virginie.
Thank you.
And see you
you.
next week.
Thank you. Thank you all.
You're welcome.